right. So this is the momentum equation. Right hand side, this is the force and this is the momentum going outside the control volume minus momentum going inside the control volume. Now we will manage these two equations in different form with the help of integration concept. Outside the boundary layer, the Bernoulli equation may be written as, for incompressible fluid, P over rho plus V square divided by 2 is equal to constant, right. In differential form, this may be written as dP over dx is equal to minus rho u infinity du infinity over dx. So dP over dx in the previous equation is written in terms of u. Then the previous equation, momentum equation, can be written and can be realigned in this manner, and finally we will get this equation. Here we have a unit integration from 0 to L, and here we have written as 0 to delta. Why? This region can be divided into two categories. This is a flat plate, this is a boundary layer, thickness at a given section, this distance is L, this distance is delta from this point to this point. So 0 to delta and delta to L. From delta to L, this u becomes capital U. So this integral u multiplied by u infinity minus u infinity square will become 0. So that is why the limits of the integration can be changed from 0 to L to 0 to delta with the help of the concept of boundary layer. Means by boundary layer we assume that at this point velocity becomes 99% of free stream velocity. That is why outside the boundary layer the velocity is capital U, right. Now this is the equation. We can solve this equation and we can find out the tau w and we can find out the delta, etc. Now how can we solve this equation? For solving this equation we must know u. How does this u vary? Right, then we can substitute this velocity profile in this equation and integrate it and get some desired value. So how do we get velocity profile? This can be evaluated with the help of some boundary conditions. What are those boundary conditions for calculating or for finding out the velocity profile inside the boundary layer? We know that at the surface, at the flat plate, at the surface, this is x coordinate, this is y coordinate. When y is equal to 0, u is equal to 0, v is equal to 0, right. When y is equal to delta at a given location, when y is equal to delta, what is velocity? Velocity becomes 99% of free stream velocity. This may be treated as u infinity. When y is equal to delta, naturally du over dy is 0. There is no variation because there is no shear stress also and there is no velocity gradient. So du over dy is equal to 0 at y is equal to delta. And when y is equal to 0, with the help of NS equation, this is the term with the help of NS equation, del 2u over del y square at y is equal to 0 is equal to 1 over mu dp over dx. If we have a flat plate, in that case dp over dx will be, if we have a flat plate, then what is d infinity over dx? What is dp over dx in case of flat plate? In case of flat plate, there is no pressure gradient in x direction. So dp over dx is 0. When dp over dx is 0, it means du infinity over dx is also 0, right. So with the help of this concept, we can say that del 2u over del y square is 0 at y is equal to 0. Right. So we have these 4 boundary conditions. We can assume the velocity profile with the help of these constants, which can be evaluated with the help of boundary condition u. U varies in this manner: a plus v by plus cy square plus dyq. So we assume such polynomial having 4 constants. These 4 constants can be evaluated with the 4 boundary conditions. So you apply these 4 boundary conditions and get these a, b, c, d, and ultimately by solving for a, b, c, d, by using those 4 boundary conditions, we will get 4 equations, and by solving those 4 equations, we will get the value of a, v, c, and d. We will get this velocity profile by substituting the value of a, b, c, d in the profile equation. U over u infinity is equal to 3 by 2 y over delta minus 1 over 2 y over delta q. Now we have the velocity profile also for these boundary conditions. Now if we want to solve the problem for getting the shear drag and boundary layer thickness with the help of von Karman's momentum integral equation, we can solve it. So in von Karman's momentum integral equation, for a flat plate, this term is 0, because du infinity over dx is 0 for flat plate. If this term is 0, then the remaining term is d over dx 0 to delta u infinity minus u square dy is equal to tau w divided by rho. So this is the equation here. If it is divided by u infinity square, then we will get the same equation which is written here. Now in this equation, substitute the value of u over u infinity from this equation, u over u infinity, this is the velocity profile. Substitute this and integrate, we will get d over dx 39 over 280 delta is equal to tau w divided by rho infinity square. Now what is tau w? Tau w is the shear stress at the wall. So for laminar flow, we have to keep this in mind, that for laminar flow, this may be written as mu du over dy, at y is equal to 0. Now how do we get du over dy? We have the velocity profile. Here we have velocity profile. Differentiate this du over dy and put y is equal to 0. We will get du over dy at y is equal to 0. So by solving that, we will get the value of tau w. Tau w is equal to 3 by 2 mu infinity over delta. Now substitute this tau w in this equation.